Hi, everyone. I'm Fan from Cornell University. I'm a fourth-year PhD working on system security and applied cryptography in general. In this talk, I will talk about resource-efficient mining, where we use trusted hardware to reduce the energy cost to build blockchain. So, okay. The word blockchain has really become a buzzword, and it also become a general concept that can mean different things to different people. Right now, there are at least two visions people have about blockchain. So one of them is the one held by the cryptocurrency community. In that vision, blockchain is primarily used to reduce centralization, so people can build decentralized currencies on top of that. Cryptocurrency community has really built a lot of coins and services around this concept, and it's still developing. So, and another view of blockchain is the one held by fintech community. Fintech or financial technology community, including those accounting firms, major banks, tech companies, or central banks, they have no interest in building another currency. Rather, they use blockchain as a distributed ledger to either facilitate existing business or to enable new type of transactions, such as IoT micropayments, etc. In this talk, we are going to focus on merging the gap between what we have and the requirement from fintech applications. In particular, we will focus on this last but not least problem, resource consumption. As we all know, proof of work, or PoUW, is a strong solution to the problem of decentralized consensus. But the proof of work is designed to consume a large amount of real-world resources. Essentially, a block in a proof of work blockchain is a proof of some real-world resource consumption. It could be the money you pay your electricity bill, or the money you buy mining devices and organize the mining farm. And moreover, this wasteful nature seems to be inherent, because that is how the system is secured. Because by doing so, we are making it hard for the attackers to attack, because attackers now have to similarly burn those resources to take over the system. So estimations may vary, but according to Digiconomist, the latest estimation of Bitcoin energy consumption is 16 terawatt-hour per year. That is the energy used by basically 1.4 million US households. For the completeness of the discussion, I would like to point out that for other settings, there are environmentally friendly alternatives. For example, for centralized settings, you can use BFT type of protocols, and there are also proof of stake type of protocols. But the POS does require a different trust assumption than proof of work. And for those protocols with complicated penalty mechanism, the convergence time of the system could be longer. There are also protocols that try to repurpose a specific useful resource to achieve consensus, such as storage or prime number. But some of them are not efficient enough, and also being useful. Something being useful is actually questionable because, for example, storage might be useful for you, but not necessarily useful for me. So the question we ask really is, can we achieve the similar guarantee of proof of work without all of the waste? In proof of work, actually, you are proving that you are doing enough useless work. But why useless? Our key idea is to do useful work instead and use that for mining. So similarly, if the attacker wants to take over the network, the attacker has to do many useful work, which is just as hard. Proof of useful work makes use of a technology called SGX. SGX stands for Software Guard Extension, which is a CPU instruction extension available since early 2016. So you can think of SGX as a secure enclave in which you can put your code and data. This enclave will protect your code from potentially malicious hosts, by which I mean you don't have to trust the application code, nor do you need to trust the operating system in order for your code to be secure. SGX guarantees both integrity and confidentiality for your enclave. It means no other software, even the operating system, can tamper with your enclave. And they cannot learn anything about the internal state of your enclave. Another important functionality of SGX is remote attestation. That allows you to remotely verify the security of the platform. Each enclave has a fingerprint, basically a hash of the code and data. And an attestation basically is a signature over that fingerprint. It's a group signature, and most importantly, the key used to sign that signature is only known to the SGX hardware. So if you can verify such a signature, you can rest assured that it is indeed that enclave with that fingerprint running a secure environment. And the building blockchains using SGX lead us to a new trust model or security model. On one hand, the blockchain is still permissionless because anyone with the SGX CPU can join. And SGX CPU are now widely available. But on the other hand, the system is only partially decentralized because we have to make trust assumptions about the manufacturer of the hardware. So basically, in a nutshell, the assumption we need to make is SGX will work as advertised. And the important detail is because Intel is the manager of the group signature we saw on the last slide, we need to assume that Intel will correctly manage the identity and the signing keys for that group signature. So within this trust model, there are actually some work in parallel with this one. The one that's mostly close to this work is a protocol from Intel called Proof of Elapsed Time, or PoUW. So the idea of PoUW is, now that we have trusted hardware, why do we need to do anything at all? So PoUW simply simulates proof of work by sleeping for a randomly selected amount of time. And they use trusted hardware to prove the correct behavior. And very nicely, this simple protocol actually achieved consensus in a partially decentralized model. And ideally, the mining cost of PoUW will be very low because for one, you can mine just using existing hardware. You don't have to buy specialized devices. And for two, you can mine while your CPU is working on something else. So we call this offhand mining. And if that is true, the mining cost is really minimum. However, as we find out, there are actually some technical challenges that are not fully addressed in PoUW. And in PoUW, the mining power of a CPU actually is not proportional to the monetary value of that CPU. In other words, an old CPU is just as powerful as a new one when it comes to mining power. So this leads to a very interesting problem as we call the stale chips problem. The problem is, in this protocol, the equilibrium of the miner's behavior is not to mine with existing hardware and not to do offhand mining, but rather to mine using old and useless devices. because all the devices are useless, this means that they will build dedicated farms for just mining. So this actually means that the actual mining cost is not low but high. This is in contrary to the original intent of PoUW. Another problem with PoUW and any SGX related application in general is, even though we assume SGX CPUs are manufactured in a secure fashion, individual ones might be broken by well-resourced adversaries. And once a single CPU is broken, it's actually become a huge problem for PoUW. Intel, in parallel with this work, Intel proposed a simple statistical test-based mitigation. But their proposal is mostly heuristic, and in particular, it cannot answer questions such as what's the advantage and what is the cost of this test. So I will come back to this later. So this insufficiency of existing solutions lead us to the idea of proof of useful work. Okay. So in proof of useful work, we replace the hash calculation in proof of work with something useful. And similarly, each unit of useful work will give the miner a chance of a Bernoulli test. And following the same reasoning as the one for proof of work, proof of useful work will generate similar exponential block interval. And as you will see later in detail. The first challenge we have when realizing the idea of proof of useful work is, how do you meter the amount of useful work? And we chose to count the number of CPU instructions executed. Right, there are a couple of reasons why we choose to count CPU instructions. First of all, although it might not be a perfect metric, we believe it's a representative metric. And most importantly, counting CPU instructions can be done in a trustworthy way with the current software and hardware we have, and without breaking the trust model of SGX. And if in the future, if better options become available, switching to that actually doesn't change the system a lot, because it's just a metric. So what's really challenging is we want to allow for arbitrary programs to be used as useful workflow. The reason for that is we don't want to define what is useful, because being useful means different things to different people. So if a malicious participant in the network can craft programs that can escape counting, then the system is broken. So we have to find a way to count CPU instruction securely and equally across arbitrary programs. And on top of that, we need to do everything in a publicly verifiable way, because we want the blockchain to be open to everyone. So the way we did it is a combination of dynamic and static program analysis. The dynamic part of it is for any given piece of program P, at the compile time, our toolchain will instrument it with so-called self-metering functionality. And and here the P prime will have the same logic as P, and in addition, it will keep counting instructions as it's being executed. This self-metering functionality will enforce a set of policy, including correct page permission and a single-threaded enclave, and etc. So for more details, you can look it up in our paper, and I'm happy to talk about it offline. So the workflow of a proof of useful work secure enclave is the following. The input is instrumented enclave, instrumented program, and a block header. The block header is the same as we have in the Bitcoin and other blockchain, basically. So first of all, the instrumented program is evaluated. that gives the same result as P. And at the end of P prime, we are now able to learn the number of instructions executed. And now the proof of useful work enclave will simulate n Bernoulli tests. And if any of them succeed, a block is mined. So as I said, because we are doing same Bernoulli test as proof of work, this procedure actually gives a similar exponentially distributed block interval. Another challenge is all of this has to be done in a publicly verifiable way. So for proof of useful work, there are two things to verify. First, we need to verify the validity of this ticket. This actually is the easy part because, as you can recall, this ticket is the output of some enclave, and its validity is covered by attestation. So we can verify its validity by checking attestation. That is sort of given. What's more interesting is we also need to verify that this P prime is correctly instrumented. Again, because we want to allow arbitrary programs to be used as useful mining work, it is actually miner's responsibility to instrument the program and use that for mining. And the miners might just choose not to, and that's what we need to catch. So in order to verify P prime is compliant to our policies, we will need the source code of P prime. So this leaves us basically a few options. We can either put all of the source code on the blockchain, but we will have scalability problem later because we want to allow for arbitrary program. Or we can also go to the other direction and only allow a predefined set of programs to be used for mining. But that is not good either, because for one, it's limiting, and for two, it introduces centralization. Because no matter who gets to decide what program is suitable for mining, that party has more power than everyone else in the system. So again, we want to allow for arbitrary P prime. So how can we work this around? We did it through a mechanism called the hierarchical attestation. So suppose there are a bunch of instrumented programs. They all generate proof of useful work, and we want to prove the validity of it without. We want to make sure everyone can verify the validity of it, but we don't want to put all of the source code on the blockchain. So we did it by adding another enclave called compliance checker. The compliance checker take as input those enclaves and check against our compliance policy. If the enclave is correctly instrumented, this compliance checker will output another attestation. Note that this attestation contains not only the fingerprint of the compliance checker, which is the black fingerprint, but also another fingerprint for the the enclaves being checked. So these two attestations together now form a complete proof of useful work. It proves not only the proof of useful work itself is valid, but also it is generated by a compliant enclave. So the final technical challenge I will talk about is what we call the broken chip problem. Again, SGX, although we assume the manufacturer of SGX is secure, the individual ones actually might be broken because SGX doesn't actually achieve perfect isolation. Although there is not yet a successful attack that breaks SGX, by breaking I mean extract the group signing key, but the side channel issue has reminded people of this potential break. So This is very bad for proof of use work in particular, because now if the SGX is broken, the broken SGX can generate proof at any time, at any rate. So basically, attacker will get paid by doing nothing. So to deal with this, we have to make an important observation. That is, by using SGX, actually we get an implicit public key infrastructure. Recall that we assume that SGX will correctly manage the signature group. It will correctly assign identities to everyone. And so it follows that even SGX, even the attacker can break SGX nodes, it cannot forge new identities, because the new identities will not be in the signature group that's managed by Intel, assuming Intel will correctly do that. So following this, we can work with the following adversarial model. The attacker may forge proof of useful work at any time, but it cannot forge identities. So this allows us to build a mitigation framework around the idea of statistical test. So the basic idea is, since the miner cannot forge identities, we can just match every miner to its fixed identity. And if a particular miner seems to be way lucky than Euro, then probably we should cut it off. So what we did actually is not just to come up with the idea, but also developed a rigorous framework so that we can reason about the efficiency and the cost of this type of mitigation. So very quickly, let me show you some results. This is the red line shows the adversarial advantage. That is the ratio between the adversarial's revenue compared to honest guy's revenue. As you can see, as time goes by, as we collect more and more data, the revenue, the advantage converges to some value close to 1. And as with any statistical test, there is a probability of false rejection. And false rejection actually incurs waste, because we are throwing away valid blocks that has hard work in it. So here, similarly, the red line is the waste incurred from false rejection. You can see that as we collect more and more data in our simulation, sorry, this is not simulation, this is actually, yeah, it is a simulation result. So it converges to 0, some value close to 0. So we've implemented everything I have talked, and we did a benchmark, end-to-end benchmark, to compare the performance with what we call native execution. Native execution refers to run the same program on Linux directly without SGX protection. So from this benchmark, our system incurs a less than 15% of runtime overhead. So to conclude, I would like to summarize briefly that we proposed a proof of a useful work that avoids waste. And we proposed a way to build blockchain on top of that, and that is called resource-efficient mining. And the system incurs a less than 15% overhead compared to native Linux execution. And in addition, we propose a solution to a broken chip problem that is not only useful for this particular protocol, but also for other applications that involves SGX. Oops. Yeah, that's all I have. Questions are welcomed.
Thanks, speaker.
Yeah, thank you very much for the talk. My name is Martin Grote. I'm from Ruhr University Bochum. I would like to know, is there a possibility to get out of an SGX enclave and maybe perform some network connection, so I can write a program which just does not attacking some servers in the internet. So that's a legitimate program in your scenario or not? So DDoS web server is okay, or?
So you're asking what kind of program we can put in SGX?
Yeah.
Technically, so SGX is an isolated environment, and it like put operating system outside of the TCP. So basically, the software cannot rely on any, cannot basically trust any operating system services. So you can write programs that use operating system, but you have to treat the return value from operating system as untrusted. That is, I think, the only limitation you need to deal with when you write any program for SGX.
I think the question was whether you do a malicious program as the mining program, right? So if P is malicious, like it's a DOS attack thing, and then you're getting other people to do attacks for you.
That's a good point. Right. Yeah. So currently, in our framework, I would say this is allowed, but DOS attack might not be very efficient in that you have to go out to operating system again and again. So that there might be some economic penalty for doing so. But technically, any program is allowed in this framework.
Actually, that's true. It's inefficient, but it's very useful to get people to jail. So that would be maybe enough. Not if you have a monetary.
Well, let's just take this offline, and you guys let's go on to the next question.
Okay.
Hello, thanks for the great talk. I was wondering, the proof of work you're using is the number of instructions, right? So if I compute instructions that take less cycles of CPU, I will have more useful work, right? So I would end up executing basically only NOPs, and I would have more chances to mine, right?
That is basically correct. So this is that's the reason why I say CPU number instructions might not be a perfect metric. So two answers to this question. So first of all, there might be some value in the output of the useful work, right? Remember that when you do useful work, you still get some output, and that output might be useful. And being useful probably means it has like monetary value. So that might be one economical reason why you don't want to use NOP to do this kind of thing. And the second of all, I think that's probably the only.
Okay, thank you.
Brian Parno from Carnegie Mellon. So my impression was that there were some previous results saying that it can be dangerous to have useful work in this kind of scenario, or to reward useful work, since if I want to attack the system, in Bitcoin today, I don't get any subsidy. Buying more machines to attack Bitcoin, there's no subsidy for that. Whereas if I'm getting benefit from buying all these machines in the first place, then what happens there?
Yes, this is indeed the problem that we considered. I think in general the answer is this protocol raises the power for both attackers and the defenders. So it is easier for everyone now to join and mining and become a miner using your existing hardware. So that in that sense, the network is secured by more and more people, which makes it more secure. But you are right that now organizations like Amazon or Google, they can just convert all of their machine into attackers and take over the network. So maybe one mitigation that we discussed in the paper is we can require, for example, to open source all of the useful program, for example, and this will maybe disencourage some of the attack from our big data provider. I think we discussed some of these issues in the paper, but I don't have time to go through it in the presentation.
You have 30 seconds for a question if you have it.
I would like to know, how do you validate results like protein folding in a fast way when you have 10 computers? So there are some problems which you can't verify very fast. So
The validation comes from the fact that it's running enclave. So if the program is correct, the output will be correct. So there's.
That's not true for all research areas, but okay, I get the point. Thanks.
All right, great. Why don't we thank Fan and all the other speakers.